a quick overview of what is Access, just to get everyone on the same page, and then in a few minutes I'll hand over to Erin, who will give you a quick overview of the science team's program for Access, which is in some sense the formalized program that we've been putting in front of NASA. But of course, most of this conference is given over to the community. Is what will you do with Access, which is really such a core, such a central part of Access. So that's what most of this conference is. But I just wanted to ground people with this. Okay, so Access is the future of X-ray astronomy. So it's high throughput, high angular resolution X-ray astronomy, and in this graphic, which is actually from our proposal, you see, is there a pointer around? No, there isn't. Okay, that works. So over here you see just a comparison of the basic characteristics of Access. So the angular resolution is the only other. Thank you. The only other mission, of course, that's comparable is Chandra, which is sub-arc second on Access. But then as you go off the axis, the aberration kicks in, and it becomes significantly poorer. So with Access, the new optical design for the mirror lets us have very high quality imaging across the entire focal plane. So 1.5 arc seconds on Access, and then very slight degradation. But of course, the key thing is our sensitivity is driven by our effective area. Have an order of magnitude more effective area than Chandra, which you can see in this graphic here. So combine that with our angular resolution, we are an incredibly powerful observatory for a lot of X-ray astrophysics. And here you see we call it our horizon plot. It's various different science, various different target classes, and how far we can study them, and how this puts us in the same ballpark as the other facilities of the 2030s. So just focusing on one example here, the massive black holes. So for AGN, with Access, we can study them out to redshift or 9 or 10. Which puts us in exactly the same territory as JMST and LISA, for example. So, okay. So briefly, how did we get here? Access was first, was born out of the mirror technology development at NASA Goddard from Will Zhang's lab, and the idea came, now is the time where we can propose a large mission based upon this new technology of the mirror that Will had developed. And so this is the meeting of the first science team here, and somewhere, very too much bleak of an angle, but Richard Moshotsky is back there, and Richard was PI of the concept, and real Richard is over there. Richard was PI of Access at this time, and we worked up the concept and put the concept in front of the Decadal Survey in 2020. This is our concept paper, and Decadal Survey was receptive to the idea of this class of mission, $1 billion class mission, and they launched off the formal process of doing a competed mission in this class. And so this is the front cover of our formal response to this, to the step one response to the NASA Pro program, and we were selected for phase A. So we're very excited about this. So let me quickly flick through the science leadership team. So this is the group of amazing individuals who have helped, who have formulated the Access science, the Access concept, and in particular formulated the science team-led science that Erin will talk about. So I don't want to spend any more time on this slide, but just to thank from the bottom of my heart these individuals. And then also we have a set of major partners that are on board with Access. And in particular, I want to highlight on the right here, these are new partners who have joined Access just in this phase A activity. MPE, who are going to lead the X-ray testing of our mirror modules. And then we have two new industrial partners, Coherent and Blue Halo, which has just been bought last week by a company called AV, but I don't have their updated logo. And they are going to actually lead up the manufacturing of our mirror. Our mirror manufacturing is a mass production problem, and so industry has to do that. Okay, so very quickly, before handing over to Erin, I just want to ground us in what the observatory looks like. So this is the current engineering drawing of the instrument itself, of the actual telescope, taking away all the spacecraft. And we have the X-ray mirror on the right here. So the X-rays come in from the right, pass through the mirror array, and then we have the camera array on the back, with the focal length here being 9 meters. So this is a big observatory. By the time you put solar panels and sunshades and the like on it, you're talking about 15 by 15 meter observatory, a big mission. The key enabling technology here is the idea of making mirrors, X-ray mirrors, from single crystal silicon, which is a very nice substrate. And this is the technology that's been developed in Will Zhang's lab, where you use blocks of silicon that you can get from the semiconductor industry. They now have foundries that grow very, very high quality silicon. And then from those blocks of silicon, you can cut out a mirror segment, you can polish it to the required levels, you can coat it with iridium, which is what we do, and you end up with a segment of mirror that can easily beat, given all the development and years of sweat that Will has put into it, beat the Chandra, the Chandra smoothness, and that's what this plot shows here. So what you do is you take that mirror segment, which of course is about 10 by 10 square centimeters, and you build it up into a full array in this kind of architecture. You put them together into a module. So an X-ray image, you have to have two reflections, a primary and a secondary reflection. So we stack them up into these mirror modules. That mirror module is about 45, 50 centimeters long. And then the mirror modules, we have 14,000 segments. They get packaged into 210 of these modules. Those modules then get tiled around into an array. The array is about 1.8 meters diameter, and then that array gets packaged up into our full mirror assembly. And that's how we'll achieve the performance of Axis. And then quickly to touch on the detector. The detector is, those of you who are familiar with the Chandra ASIS, it's sort of the next evolution of ASIS with fast readout, low noise CCD chips from MIT Lincoln Labs that is then put together in an assembly, primarily whose job it is to keep those chips really nice and clean. That's the main job of this assembly. And one change, those of you who have tracked Axis for a while, one of the major changes we've made in the past. Are you having a problem with that? Okay, good. One of the major changes we've made during phase A earlier this year was an orbit change. And the principal reason for the orbit change was to make everything easier for the technology. Being low Earth orbit is actually a pretty unstable place in terms of coming in and out of the sunlight all the time. You're being heated and then you're in cool, you're hot and cool. This makes some of the mirror issues challenging. So we decided to go to L2. Thank you. And this is, can I play this? This shows how we get to L2. I love this graphic. So we launch, we go through what's called phasing loops. You'll notice the moon going around. And then the smart people in flight dynamics have figured out how to do that. And that pushes us out into L2. And so we will spend our mission life out at the Sun-Earth L2, about 1.5 million kilometers from the Earth. And one of the big advantages of that is we now have an enormous field of regard. So this is a cartoon of the Axis spacecraft, more or less what we think it would look like. But we can look anywhere in the sky apart from this cone that includes the sun and the Earth. You know, we can't look too close to the sun because we need to keep the mirror nice in shade. But we now have this enormous field of regard. So this becomes a very powerful, combine that with our ability to repoint quite quickly and our ability to have 24-hour communications with the satellite, you know, not 24 hours every day, but still, you know, we can have pretty good communications. This makes it a very powerful time domain facility. Okay, so we're super excited about this. Axis is a real possibility. We hope that this placeholder here on the fleet chart that says probes will soon say Axis, and then, you know, the community can dive in and do your best with it. So let me hand over to Erin, who will tell you just briefly about the science team's program. Erin. And how do I quit out of this? End show. This one?
Thanks. So I'm going to try and go quickly and tell you a little bit about the Axis Science Program. This is the directed science program, so this is just an overview of some specs in case you haven't been living and breathing Axis every day for the past 5 years. So soft X-ray 0.3 to 10 keV, readout of 5 frames per second, with a goal of 20 frames per second. So with this larger effective area, but also with the faster readout, we should have a pile-up limit similar to that of Chandra, somewhere around 10 to the minus 12. We have a fast slew, and as Chris was just saying, this enables, you know, with our large field of regard, 85% field of regard, we have a very fast TOO response time. So we'll have the ability to get on target in less than 1 hour, 70% of the time. And really the limitation there is, you know, how quickly can you slew to an object? If you're in contact with the observatory, it's just how quickly can you slew to the object. So even that 1 hour is like pretty easy to achieve 70% of the time. And we can get on target within minutes in some cases, depending on where you are in the sky. So what I want to tell you a little bit about today is the Axis PI-led science. So NASA has told us, has given us in the announcement of opportunity for this program, it said design, we would like the science, you know, the Axis prime science team to design 30% of what Axis will look at. But during that 5-year mission lifetime, 70% of the observing time is for the general guest observer. So there's no proprietary time on any of this data. And immediately guest observers are going to be having access to the observatory. So what we've decided to do with the 30%, the PI-led science, is do a lot of the science that is just going to be really hard to get through a guest observer program. So like big surveys that take many, many megaseconds, that would be hard to get through a guest observer program. We're going to be doing those through the PI-led science. So I want to tell you a little bit about that. These are our Axis science pillars, and they're based off of major questions that were kind of given to us, you know, decided by the community by the Astro 2020 Decadal Survey. The first pillar is, what are the seeds of supermassive black holes and how do they grow? How do gas and metals and dust flow through into and out of galaxies? And so this is just like feedback, both stellar feedback and AGN feedback in galaxies. And what powers the diversity of explosive phenomenon. So we have a strong time domain multi-messenger component as well. So I want to tell you a little bit about these, first, these deep extragalactic surveys. This is just a snapshot of that deep survey, and you can see all of those AGN in that, that's the circle there is one, the field of view of Axis. And so you can see lots of AGN at different redshifts. You can see clusters of galaxies. And on the right there, you're seeing one of these like kind of sensitivity versus the area of the survey. And so we're a factor of 10 deeper than Chandra over a much, much wider area. So why are we doing these deep surveys? The prime question here is, what are the seeds of supermassive black holes? So this is an objective led by Nico Capilouti and based off of simulations that Angelo Ricarte did in the front row there. And the idea is that we see these supermassive black holes, millions to billions of times of the mass of the sun. They sit at the centers of all galaxies. Even when we look to the highest redshifts, we're seeing that they're still a billion times the mass of the sun. And the question is, how did they form? From light seeds, something like 100 times the mass of the sun, that's a black hole that will grow very quickly and accrete at super Eddington rates. Or did you start from more massive seeds, something like 1,000,000 times the mass of the sun through a direct collapse scenario, and then only has to accrete at sub-Eddington rates? This is a major question in modern astrophysics. And the idea is that, in order to kind of distinguish between these two scenarios, you have to probe further redshifts, back earlier in time than we currently can. And so looking at the X-ray luminosity functions at high redshifts, for these heavy and light seed scenarios, they start to differ once you get beyond a redshift of 8. And so the goal is to get out to a redshift of 10 with Axis, where you see really at these very high redshifts, then that's where you'll see a very different luminosity function if you're dominated by heavy seeding. But there's so much more that you can do with these data. And again, everything goes public immediately. So, what would you use the extragalactic survey for? This is a plot that I love that Chris put together of the different kinds of the spectral quality that you'll see for like galaxy clusters, obscured AGN, spinning black holes. You can do iron line measurements we'll hear about later today. And these are all at a redshift of like 2 to 3. And it's just kind of amazing. This is like new star quality spectra, right, at a redshift of 3. So moving on to the second pillar here, this is just a kind of mad dash. One of the kind of legacies of Chandra, right, has been studying AGN feedback in clusters of galaxy, where you can really map out the effect of jets that inflate these cavities in the ICM that you can map out in X-rays, right? And what we want to do with Axis now is going beyond the most massive systems, these clusters of galaxies, but can we see AGN feedback in individual galaxies? We know that this must be important, and yet it's very hard to see the effects of AGN feedback in individual galaxies. So the goal here is to look at Milky Way mass, elliptical galaxies that are, the mass of our Milky Way, kind of typical systems, to see the effects of AGN feedback in action. And so this is a simulation from our step 1 proposal. What you need to do is not just image these elliptical galaxies, but you need to be able to map, the temperature profile, looking for, shocks in the ISM. And so, this is just a comparison. So you need both, spatial resolution, but you also need large effective area. You need enough counts to be able to do that spectral analysis on, over a wide field. So this is showing the comparison of Chandra on the left to Axis in the middle. If you bin those data to require at least 1,000 counts in each of those bins. So you can do some kind of spectral analysis, and you can just see the difference there. Just we have so many more counts with Axis. And you can see those jet cavities in that central image. And then you can do spectral analysis to see how does the temperature change, pick out those shock fronts in those systems to see really how is the AGN affecting the ice. So finally, just one little bit on our time domain pillar. One of the things that I think is like crazy is, we see supernovae like almost like every day now, right? Time domain surveys are discovering these supernova explosions, and yet in like more than 50% of the cases, we actually don't know what was the progenitor star that led to that supernova explosion. And it turns out that the X-rays are a signature. The first light that you see from a supernova explosion will come in X-rays. It's called a supernova shock breakout. As the star expands, finally, the first light that you will see escape will be in the X-ray band. And that X-ray flash directly encodes information on what the progenitor star was, how big it was, and you can see, what was the progenitor of these stellar explosions. And so Axis has a large, field of view, has good sensitivity across that field of view, and has a transient alert monitor that will pick out these flashes and alert the community within something like 10 minutes. And so we'll be able to measure these shock breakouts. So far, there's only been one ever discovered, and it was just through a serendipitous observation. Swift was pointing and just happened to see one of these. And now we will start detecting these in real time, seeing something like 50 in its prime mission, and out to close to the peak of star formation. So in addition to that exciting time domain capability, the other thing, the other kind of big exposure campaign that we're doing in the PI-led science is a galactic plane survey. And this is very complementary to the Roman galactic plane survey. So it's both the plane and the bulge. And you can see it's 10 times deeper than what's been done previously, 5 times larger area than what has been done previously. So we're talking about 1 million new objects in the galactic plane. And more than that, this is going to be a time domain survey. We're going to come back to these points several times throughout the mission. And actually the cadence of that is still like being discussed, and something we'd like to, feedback from the community on, like what would be most useful for your galactic plane survey science. So as we said, like the rest of the time, 70% of the time is for the guest observer. And this is, I think, what we're going to be hearing about the rest of this conference. So we've had a huge outpouring of support from the community. So thank you all. I think really what we need to show is that this is a mission that's not just for even X-ray astronomers, but it's for the entire astronomical community. This is a big observatory. It's really important that we show, broad support. So we've put together, Mike Koss has really been leading this effort, these geoscience investigations, and we're putting it together. I think it's going to be like 500 pages, and this was made by ChatGPT, but really what I think we need to do is like bind it and print it and like bring it to site visit and like show them how huge, like all the science that we can do. And so thanks everyone. The final deadline for geo investigations is May 30th, and we're going to post to archive and hopefully incorporate some of that into the Axis proposal that we submit. All right, so I will leave it there, and happy to take any questions. Chris can come back up for questions as well. Thanks.
into the formation of the first black holes. We just heard about some of the really interesting science that Axis is hoping to do, and I think Priya is going to have some exciting things to tell us as soon as we get the computer up and working.
Something with still.
Okay, because we're scared. We're sharing that.
Yep.
Are we there?
Yes.
Okay. Oh, terrific.
Ooh, yeah.
Just go to share next.
That often is a computer dependent thing. I have unfortunately been learning that teaching the last few years, so because I rely on presenter tools, but don't necessarily want the students to see it.
Yeah, especially I often put like little caddy remarks to myself.
Yeah, I
Snarky.
don't do that myself, but everybody, yeah.
How many astronomers does it take?
That looks good? Okay, great.
Okay, terrific.
Perfect.
Yeah.
All right, Priya.
Yeah, great. So first of all, I want to say thank you very much to the organizers and for the Access team for inviting me to talk today. It's been absolutely wonderful to see this mission kind of coming to life. And I was just talking to Richard earlier that I was part of a very early convening, a meeting in Washington, D.C. at Carnegie observatories talking about Axis and what all it might do scientifically way back when at stage 2 of this process. I'm thrilled that it's now in phase A, and I think much of what I want to talk about today is sort of new opportunity space that is opening up for the wonderful science cases that are already rich for Axis. And I think much of that, this was anticipated, right? So you always anticipate synergy in multi-wavelength studies between observatories both in space and on the ground. And so what I want to share today is things that we are really learning from JWST, but have very deep implications for our understanding of the formation of the first black holes, growth mechanisms, and therefore it has very important implications, very exciting implications, and very exciting new opportunities for Axis. So I just want to give a shout out to a lot of people who've been working on sort of the first collapsed objects, seeds for black holes over the years. And I think one thing I can say, there's a lot of, much of this field, right? There's a lot going on. There's a lot of debate. And as you all know, with many of the exciting JWST results that are coming down, there really isn't consensus yet on many issues. And I'm sort of stating that up front so that when I make some claims, I'm going to claim that it's substantiated by a set of observations, and there are others and there are other possibilities, and everyone keeps an open mind about it. But the one thing we are all agreed on, regardless of which mission we're working on, the consensus is on what some of the big fundamental open questions are. And in particular, with regard to, I'm focusing here on the origin and growth of supermassive black holes. And so how do the first seeds form? And so it turns out that there are many candidates that keep emerging, sort of, resurrected, die, then re-emerge. And so primordial black holes and direct collapse black holes that might form, not quite primordial, but quite early, at redshifts of 100 or so. Some very interesting theoretical work that's coming down the pike that shows that those kinds of seed formation is not to be discarded as too speculative at this point. And of course, we all know about light and heavy seeds. And of course, the fundamental question is whether the stars come before the black hole, or do they co-form and co-evolve, and when does that co-evolution get set up? And one of the fundamental questions that I think AXIS is really well poised to understand, aside from the origin question, is the growth mechanisms. And the growth mechanisms, whether you have standard growth, accelerated growth, because it's becoming very clear that accretion is most likely drives the growth of supermassive black holes. Mergers are important. They are important in very specific cosmic epochs and in very specific cosmic environments. And of course, this issue of feedback. And I think that Erin already showed that, the pillars are sort of here, right, in terms of many of the questions. So there is, as you all know, a supermassive black hole revolution that has begun. And what's been really exciting is that the nanograv signal for the stochastic gravitational wave background. And I think it's an open question whether the inferred amplitude is consistent with current models for supermassive black hole growth, quasars, and I think that there's a lot of interesting work showing that most likely it is compatible. Originally, it was claimed to be. And then on the theoretical side, one of the biggest open questions has been how gas actually makes it down to horizon scales for a black hole from very large scales, megaparsec, kiloparsec scales. And you might think this is a question that ought to have been settled by now. It's not, and it's not been settled at all because of the numerical challenges involved. And now what's exciting is many groups around the country are looking at this problem. So connecting gas flows, inflow and outflow, simultaneously tracking it at kiloparsec scales, Bondi radius, which 10 to the 5, 10 to the 6 RG, all the way down to the horizon. And I think the early results are super exciting, and it's very clear that not all simulations, simulation work to date assumes that any gas packet, due to resolution effects and computational difficulties, any gas packet that crosses the Bondi radius essentially makes it to the horizon. And it turns out a very small fraction of it actually makes it down to the horizon. And this is very, very important for sort of calibrating our understanding of what are the luminosities that we can expect from accretion, which is directly relevant to what AXIS. But it's all good news for AXIS as far as I can tell. In fact, very, very promising. I think the JWST results on, so this is also early days for JWST, right? So we're just starting, that window is just opening. So JWST has opened this redshift greater than 10 window, and we're starting to see the very first black holes right now, a handful of them, but very soon, hopefully, we'll start discovering and filling in a population. So what has really been super exciting is we are starting to directly image quasars and their hosts at redshift 7 or so. We're starting to detect a whole class of objects. Okay, there's so much talk about LRDs that I decided not to have a slide and not to have them sort of on the page, but they are very, very interesting objects. And the debate is still raging on whether we think that the flux that you see, what fraction of the flux is coming from the presence of an accreting black hole versus a stellar component. And as I'll show you in a little bit, there is growing compelling evidence that perhaps they may be revealing a new formation pathway for black hole seeds. And that new formation pathway is very good news for AXIS because we believe that that can operate not just at the highest redshifts, but at intermediate and perhaps even lower redshifts. And there's some emerging evidence. We have a paper with some data that I cannot actually talk a lot about, but I will allude to it. in a moment. So what has really happened recently with JWST? So this is just a plot that's showing you the gray areas SDSS, the contours that you see, and the solid filled symbols are JWST detections of black holes. And you can see that it's starting to fill in a space, edging out to higher and higher redshifts. So this is sort of a space that was inaccessible to us earlier, and we are starting to fill in. And filling in the space has really important implications for early black hole formation and growth, because I think the perennial sort of question is whether you need heavy seeds in the early universe, or whether light seeds can be actually amplified by super Eddington accretion episodes, fairly short-lived but fairly frequent. And the issue is still raging. For some candidates, I would say that it's fairly settled, that the amount of fine-tuning that would be needed with that kind of light seed and episodic super Eddington accretion is just not as viable as an explanation. And regardless, I should just really put it out there that one of the big open questions I really think where we are still all battling is, in my opinion, we still do not understand what a source accreting at super Eddington looks like. It's multi-wavelength SED. We don't know what that spectrum looks like. It's very unsettled. It's very controversial. So I think that, and I don't believe that we have quite yet seen a super Eddington source conclusively. Anyway, coming back to seeds, and I think as you all know from the work that's been done by Angelo for very axis-specific predictions, it's really looking at these various channels, light seeds versus heavy seeds. And I want to insert here this new sort of new set of pathways. So there's direct collapse, heavy seeds, and I'll show you there are many ways to get direct collapse, which is very interesting. So it tells you that it's quite feasible. There are many possible pathways to have direct collapse at various cosmic epochs. And then POP3, of course, is, again, a reliable source for light seeds. And once again, I can only mention that we may have detected the first cluster of POP3 stars, and many more to come, I'm sure. So I think what has really emerged recently, from the theoretical point of view, it was always super exciting, which is nuclear star clusters as incubators for the formation of seeds. So recent theoretical work by my group and several other groups has shown that nuclear star clusters can give you seeds of various masses. And what is unique about them is that they can be incubators for seed formation throughout cosmic time. And I think that's where this is a huge opportunity for Axis. We actually believe that you can start seeing seeds that form at epochs redshifts of 4, perhaps even 3 in nuclear star clusters. And as I mentioned, we have a candidate at redshift 4-ish, where we see some evidence for an underlying faint stellar population and a very actively accreting supermassive black hole in place. Sort of clearly indicating that the nuclear star cluster is most likely the birthplace for this supermassive black hole. So let me just go back to direct collapse and show you that direct collapse can occur many ways, and that is also good news. And it turns out that theorists have been looking at various scenarios and physical pictures where direct collapse can be effected, not just at the highest redshift, but at intermediate redshifts. So you've seen, so I'll just run through a couple of the scenarios just to show you that there's a rich phenomenology that people are busy calculating observational signatures for. Most of these scenarios do not yet have a full observational signature, i.e. a computed multi-wavelength spectrum for what these sources ought to look like, and hence strategies on how to look for them. So one of these early high redshift models is from turbulent cold flows that you expect to be a natural consequence of galaxy formation. So the other one is the one that I and my group have really worked on for a long time, and this is direct collapse of pre-galactic disks. And the reason I personally think this is exciting is, as I said, we've closed the arc from the theoretical toy model all the way to the observables, and now we have a couple of candidates that actually satisfy all the criteria that we worked out in 2017. So that's why this particular channel is exciting, because we've already closed the loop in terms of going to predictions. So there's another kind of riff on our scenario, which has to do with the fact that a direct collapse black hole can form in these very early halos, but it might be embedded in a big sort of H2 region. And such in this mode, you would be detectable for a brief period of time in JWST. So not totally viable, but you never know, right? You may detect, so there's a sort of up to a point evolved signature that's been predicted. Then at lower redshifts of 8 and perhaps even for down to redshifts at 6, numerical simulations are showing that during very major gas-rich mergers, even if these galaxies are not already seeded with black holes, you could actually form direct collapse. You form a very supermassive gas disk that has nowhere to go but to form a direct collapse black hole. And so these are, again, making predictions for formation of heavy seeds at later times. So this increases the overall number of black holes. And I want you to keep that in mind, because that's something very interesting that JWST is telling us, that we do not have a complete census yet. And therefore, many more black holes remain to be uncovered, especially in the X-ray. Okay. So coming back to nuclear star clusters as incubators, so there are two classes of models that people have looked at. And one is starting with a light seed and amplifying them to form heavier seeds in a gas-rich nuclear star cluster. That requires, that we believe is a pathway that will work at early high redshifts, because you want to suppress the feedback from this rapidly growing black hole to actually have mass assembly of this black hole. You require the gas to be primordial. You want to not have cooling, catastrophic cooling. And there are other scenarios in which you can look at a light black hole that scatters off the stars and over cosmic time can lead to seeds of various masses. And so this picture has become very, very interesting recently, as I mentioned, with the detection of a particular candidate that appears to ratify this picture of black hole seed formation. So I want to quickly go to the direct collapse scenario, the specific scenario that we have worked on for a while. And as I noted, what is particular about the scenario is the range of predictions as a function of time as this physical process kind of evolves, if this actually operates in the universe. And it appears that there is some, I would say, compelling evidence that this process happens. So it's a very specific cosmic setting. And what this allows is, this specific cosmic setting allows us to therefore predict very clear signatures that relate the properties of the growing black hole to its host galaxy. So that's the key, right? So the only way we are able to test seeding scenarios is by actually relating the properties of the black hole, i.e. the mass, to the larger environment in which that black hole finds itself. So we predicted that there is a sort of a transient stage, an overmassive black hole galaxy that results if you have a heavy seed that forms from direct collapse. And in 2023, the object U8Z1 and later G8Z9, these two objects, appear to satisfy all the criteria that were predicted for such sources. And what is very interesting now is that now with these two sources having found, there's an exciting time here in cosmic epoch where the scaling relations, i.e. this black hole, these are the local scaling relations, the M sigma relations, where the black hole mass is subdominant compared to the mass of the stars. That's where you end up. And if heavy seeds, and there's now, as I said, some evidence that heavy seed formation might be happening, then there's a period in cosmic time where this starts to flip, where the accretion onto the black hole will not dominate the spectrum, will become subdominant, dominant, but that can actually, that's a real rich space for tracking for axis. This real evolution, a fundamental evolution in the nature of sources. And, as we'll see, that this region between 10 and 6 is going to be filled in by other mechanisms that form seeds as well. So you don't have to rely on just finding the highest redshift seeds that are going through that phase. Direct collapse black holes in all the manifestation, all the settings that they actually occur in, are going to give you overmassive black hole seeds for a period of time, black holes for a period of time. And that period of time has now, that window is moving down in redshift and therefore getting really accessible. So this is just to show you the work that was done by Fabio Pacucci, Angelo Ricarte, and Nico Capelluti. Angelo and Nico are in the audience. So these are the sets of predictions that were made for UHZ1 that satisfied all of them, including critically this ratio between the X-ray and the infrared flux. Okay, so what are these JWST findings that I think are going to transform in terms of what Access can find? So as I said, first is this transition, the transition from overmassive to getting onto local relations, right? And I think that transition can be seen in real time by Access because you'll be starting to find sources. At least that's what our current theoretical models suggest. And these scaling relations are related to seeding signatures, but they also tell us more about the growth history and the mechanisms that drive the growth history. So if you look, for example, at two sets of simulations which currently implement seeding only at very early epochs, then you find that by redshift 6, you don't have clear-cut signatures of seeding. However, if seeding proceeds continuously, which is not yet implemented by anybody, then there's going to be lots of exciting sources to find, signatures to unravel. So my group has started working on this, and I think we won't make the May or the June Access book, but I mean, we'll be out there making predictions, bolstering the case for the really exciting stuff that Access can do. And at some level, I really like this graphic that Angelo made from his thesis work. And what you can see are this, visually you can see there's a transition that's happening to getting onto this local relation. And those intermediate stages where the transition happens, so this was a visualization of just heavy seeds, right, Angelo? This was just heavy seeds, starting just with heavy seeds. And so you see that transition, and I think Access can map out every stage of that transition. Because you're going to start out being X-ray bright, and then you will eventually get dimmer and dimmer as your stellar component starts to dominate. So I think there's a really exciting opportunity here. It's become very, very clear from the many seeding models that are out there and our expectations of seeding proceeding over time. So right now we have these two sources at redshift 10 that have been detected in the X-ray as well with Chandra and JWST. And then we have a galaxy GNZ9, which we know has an AGN, but it's not been detected in the X-ray. So I think that we've all been looking at trying to see, so, this is very nice work that has been submitted, sort of revealing what Access can do. And I just want to point out that this region is going to see a lot more action that is going to be Access detectable. And we know it's there now. So we know there have to be sources there, and we can start predicting exactly what their properties are going to be. So the other thing that's exciting for Access is that James Webb is showing that black holes are 100 times more abundant than predicted. And we're talking in, dominantly in redshifts of 4 to 7, okay? There are a lot more sources that are out there waiting to be detected. And I think the properties of these sources and how X-ray bright they're going to be is something that is actively being worked on, right? So this is where I mentioned that LRDs, these little red dots, it may turn out that they are an important phase in black hole growth for nearly all sources, right? They're so abundant that we now believe, well, at least theorists are starting to believe that perhaps we can make a case that they may be an important phase. If that is so, the current phase of LRDs detected by JWST are actually X-ray dim. At least that's our recent work led by Tonima Anana shows that the current crop of LRDs detected in this particular phase are actually X-ray dim. But if this is a phase, we know that the transition has to happen to an X-ray bright phase. And so that is going to give us many more sources that, and they won't be long-lived sources, which is why, so I mean, right now we are all debating why has Chandra not seen these sources, right? Why are they too faint for Chandra? So it's an open question, but I think there are many, many interesting opportunities. So, you know, I think what is really going to happen that is super exciting is as in the next couple of years, as we have a little more JWST data, I can promise you that this end is going to rise up. And so you're going to have many more sources that Axis can detect. So these are from predictions from a paper by Melanie Habusit and others. And what I want to show you is that, you know, at these redshifts of 3.5 to 4 and beyond to 6, there are going to be new kinds of sources that are going to become detectable. And I firmly believe that these are tied to black hole formation and growth scenarios that have to do with nuclear star clusters. And we're just starting to find, and the other area that is really promising, I think, is the black hole occupation fraction. And I think Axis can do a really interesting and important job in constraining the occupation fraction. This is a plot for redshift 0, but I think the occupation fraction, with what I believe Axis capabilities are, we should be able to have a plot like this for redshift 0.5, redshift 1, 1.5. And this is a very simple statistic that once again allows you to triangulate and say something about seeding and the prevalence of black holes overall and their growth histories. So the question is, and I remain, I mean, you know, as I said, I showed you the Pope white smoke coming from some of the questions. There are many questions that are unsettled. And the most important one, in my opinion, is still, what about super Eddington accretion? Have we seen super Eddington accretion? Do we know what to look for and what are the signatures? And in my opinion, this is the big unsolved problem for us theorists to understand. There isn't consensus yet. There have been claims for particular objects being super Eddington sources. Some have come, some have gone. So I think this is a fundamental question that is going to have a real bearing on all the sort of points that I made about, you know, the abundance, expected overabundance of supermassive black holes littered across cosmic time. So I just want to close with what I think are exciting new opportunities for X-ray signatures. And I want to invite more people to start working and trying to understand these. I think we need to see the implications for multiple seeding mechanisms that operate throughout cosmic time, which will give us potential seeding signatures at 6, at redshift 4. And these are very accessible to Axis. And I'm personally most excited right now about nuclear star clusters as the incubators, so, and the X-ray signatures for these processes. So I think that the predictions and the expectations and the prospects that have been made for Axis at this point, within a year's time, we are going to exceed even those and have very, very exciting discovery opportunities. So I'll just stop there and open for questions. Thank you.
Thanks, Priya. I have a question. So, about UHZ1. So, there are. I mean, the community is a bit skeptical on the X-ray detection of this source, or how the results would, your conclusion will change without any X-ray information on this source.
Yeah, so I think that I actually, I don't think that there is reason for skepticism, because when we published, we had 80% of the data in hand from Chandra. And we now have the full data, and therefore the significance is no longer 4.6 sigma, but we claim it's actually above 5 sigma at this point. So, I mean, if 5 sigma is the gold standard for everybody, it's the standard for us too, right? So I actually believe that we have compelling evidence for the source. I think the additional properties that have to do with, so, you know, there have been papers where people have looked at primordial black hole seeds that could have formed. Could they explain UHZ1? The question is, can you explain the properties of the the host that is hosting, the colors of that host? And they cannot. They cannot do that with either primordial black holes or with light seeds. So I think the point is that if there is going to be a concrete prediction that actually discriminates with the existing color diagnostics that we have, that you helped produce, right? Then I'm open to the idea. But as far as what we have in hand at the moment, and I believe the X-ray data for both UHZ1 and GHZ9, we've not claimed X-ray detections. There's some marginal detections at 3 sigma level for many other sources, but we have not actually claimed, these are the two sort of, I think these are very compelling. And the other attempts, so, you know, Rafaela Schneider and her group have tried to model UHZ1, the properties of UHZ1 and its host galaxy, requires a lot of fine tuning of very perfectly timed star formation episodes and mass converted into stellar mass. And so it's not clear. I would say that the evidence is compelling, and I would say, I mean, and I know that the X-ray detection is past 5 sigma now. It's 5.2 sigma.
Thanks.
Yeah, so my question is about the LRDs. Has there been many advances in sort of other theoretical models for those broad lines not being produced from AGN? Not being produced from AGN?
Yeah, so, you know, the spectral properties are so peculiar that you really have to contrive star formation scenarios to account for the full spectrum with just stars, right? So the bomber, I mean, just the breaks, I mean, it's just really hard to explain the slopes and the breaks that are seen and the colors with just a stellar population. Once again, you need to really fine tune the kind of dust and the, you know, grain size, and which is just too baroque, and it doesn't translate between LRD and LRD. So you have to develop a really customized model for each LRD. Therefore, it's very clear that some fraction of the flux, if not most of it, is likely coming from an accreting. As I said, the word, you know, it's an open question at the moment. But I think the scenarios to form these LRDs, the fact that, you know, they're extremely dense stellar component in which you could form either from direct collapse, you know, in ab initio, or from light seeds, those models are looking compelling. And as I said, there is one candidate where we have imaged the stellar component as well. And there are limits, therefore, on the stellar mass, which are, you know, again, it's one object, but it looks like the stellar mass alone is actually insignificant compared to what we should get from the accreting black hole. So right now, there are actually, you know, maybe 3 cases, maybe 3 other cases. And for 2 of the other ones, we are looking for a director's discretionary time, but one of them looks very interesting.
Hi, Priya. Well, first, thank you very much for a fantastic talk. Very exciting, of course, as you know. I was wondering about the X-ray beam claim that LRDs are X-ray beam. From the theoretical point of view, is it possible to explain both the X-ray beam and the X-ray bright populations from a single origin, from the single direct collapse, or is there any fundamental physical difference?
Yeah, that's a great question. I think that we're settling now. It's not settled. Question is not settled. These are the debates. So we had a workshop at Yale in October, the Tinsley workshop. And we ended up didn't intend to talk about LRDs, but the whole thing was really about the nature of LRDs and very spirited arguments. So yes, I think as a theorist, I would claim, and not substantiated yet with any data, that, as I said, these are various stages, but that they might transmit the formation of the formation mechanism. So the X-ray bright might be direct collapse, and the X-ray faint ones might actually be rapid amplification of light seeds. So that's sort of where we are going. And I think that there is general agreement that they are not one thing, that this whole class of objects, LRDs might actually be a misnomer as a categorization, that there are classes of objects there at different stages of both how seeds formed and how they're growing. Yeah.
Richard?
Yeah, so as Erin showed, we have a rather simple graph, the proposal about the evolution of types of objects. You're showing a much richer,
Yes.
complex environment. We have to come up with some way.
Yes. Absolutely. Yeah, we've been thinking about it because we really want to help the access case. But on the other hand, as I said, there's so many open questions and it's somewhat controversial. But what I am hoping to give to you all is by the end of the summer, we hope to at least have a schematic with some kind of, data limits, at least showing that if you had continuous black hole formation, what that plot that you have, that very nice, detection plot that you have, how we could fill that in. And I think if anything, we can, instead of having these one set of growth curves, because we have this one or two other sources, we can start filling in, other sets of overlapping growth curves on this to show.
If I could add to that, I mean, you're talking about Z8, Z9, Z10. And one of the things that we're beginning to see with JWST is that it goes back further than that, right?
Of course.
So, well, but that's exactly the point, because you're talking about what the difference between light seeds and heavy seeds are and what the environment is. At Z of 8, it's one thing. At Z of 12, it's another thing. At Z of 20, it's another thing entirely.
Absolutely.
And just the first few years of data, we're already seeing Z of 13, Z of 14 with JWST. Z of 20 is not far behind.
I'm hoping that we'll at least see us. I don't know. I'll be happy with 16 because for me, 16 is a sweet spot in terms of many of these models, as it turns out. And yeah, I don't know what 20, but I think we're likely to see 16, hopefully, right? But I think coming to Richard's point, I think I'm hoping that, my research group can help you fill in a little bit more here and extend it further down to show that there are populations even below redshift 6 that are as yet undetected, that you may, at least JWST is suggesting that you can start filling in sort of seeding signatures. So anyway, yes, I'm hoping to be more sort of concretely helpful to build the access case.
All right, let's give Priya the hand.
All right, hello everybody. My name is, the thing's up there. Yes,
Mouse.
disappeared. Yeah, that's just an example.
Yeah, because I want to move the. Oh, you could.
Yeah, can we just minimize that?
Yeah,
There we go.
there we go. Okay.
All right, my name is Angelo Ricarte. I'm a postdoc at Harvard University's Black Hole Initiative, and I work on the formation and evolution of supermassive black holes from event horizon to cosmological scales. Today I'll be telling you about a semi-analytic model called Serotina, which we've been using to make predictions for AXIS and connects with many of AXIS's science cases. So a semi-analytic model, of which I think we'll be able to hear about a few more later today, self-consistently and rapidly produces a suite of many different observables in an efficient framework. The idea here is we start off with a dark matter merger tree, assume things about black hole galaxy coevolution, and can make different contrasting assumptions about seeding, accretion, and dynamics to make a large volume of different predictions at the same time, allowing you to break degeneracies. In the era of large cosmological simulations, I actually think that SAMs are making a little bit of a comeback. They're useful if you want to efficiently model large volumes and small halos simultaneously, which is very challenging for, say, direct n-body simulations, and are also very useful when you just know less about your underlying population. And that's been very useful in the JWST era, for example. Of all of these different implementations, the area that I have focused most on is in accretion. And this is because I also work on the Event Horizon Telescope and GRMHD simulations. The latest upgrade that I've implemented into the model has been to take into account some of the insights we've obtained at the Event Horizon. And one of those is a preference for what we call a magnetically arrested disk, or a MAD. This is a model where the magnetic field in the accretion disk has become dynamically important, making some transformative effects on the disk dynamics, and is directly implicated in jet launching via what's called the Blandford-Znayak mechanism. This kind of model is favored by EHT observations, especially when we account for polarimetry, and has been shown to be pretty common in simulations, ranging from a variety of different initial conditions, including magnetized Bondi accretion, winds coming off of the stars at the center of our galaxy, zoom-ins onto quasars. All of these seem to be leading towards strong magnetic fields. This is in contrast with what we call standard and normal evolution, or sane, making mad versus sane one of the cutest dichotomies in the field. So some insights that I've implemented from this model is that the jet power, according to Blandford-Znayak, is proportional to the square of the magnetic flux, as well as the spin. And this directly ties spin evolution to the feedback in ways that we can test in a variety of different ways that AXIS is actually probing in different contexts. And I've implemented some self-consistent spin evolution formulae in order to take this into account. Here's an example of Serotina in action on a 10 to the 14 solar mass galaxy cluster. In the very early universe, I've initialized them with heavy seeds with a spin of 0, where spin is encoded in the colors here. And as the universe evolves, these black holes are going to be growing onto the M-sigma relation. And when accretion occurs, where I've prescribed some things about black hole galaxy coevolution, that accretion, as well as those black hole mergers, are going to be modifying those spin values. And this is all using new accretion recipes from MAD GRMHD simulations. So now I'll show you some predictions for various outputs of the model, starting with luminosity functions, although sorry that apparently this is the third version of this you're seeing in just the last hour. Here we're looking at luminosity functions past redshift of 6. And the point is that at that frontier from optical quasars at the time of publication, this was 2018, these different models are all lying on top of each other. But if you go further back in time, they start to diverge, where the heavy seeds in blue and purple have more of these higher luminosity objects than the light seeds. The signal here is actually pretty clean, that the heavy seeds in this Eddington limited model are able to shine at higher luminosities earlier because their higher mass allowed them to have larger Eddington luminosities at that epoch. Super Eddington, which is now becoming a popular explanation for LRDs in particular can potentially obfuscate the signal. And this means that we want to break degeneracies in a variety of different ways, which I'll be touching on today as well. One thing that Serotina also predicts self-consistently is black hole feedback. And I think even on the science team, you probably haven't seen this plot for me. What I'm showing you here is the kinetic power density, so watts per megaparsec cubed of jets that are predicted in this model, self-consistently with this kind of mad accretion paradigm. We have two different models here, where in this mad coherent case, prograde black holes tend to stay prograde, and so the spins are going to be relatively high. In the incoherent case, I'm saying that black hole accretion disk will flip from prograde to retrograde on short timescales, and the only way to get spin is to have a black hole merger. More spin gives you more jets, and so this model ends up with more feedback overall that we're planning to probe via these X-ray cavities that Axis will allow us to directly resolve, now out to redshift of 2 or so. The current observational constraints shown in gray here come from luminosity functions in the radio, but because the conversion between jet power and radioluminosity is so theoretically uncertain, there's such a wide range here that you can't distinguish these two, whereas Axis will be able to track this cosmic evolution in the most massive clusters, which is the exact kind of object where this feedback is the most important and best understood in terms of jets connected to maintenance mode feedback. Now, another thing that I'm very interested in is the ability for Axis to measure spins out to redshift of 3 or so. At present, there are 50-ish black hole spin measurements from X-ray reflection spectroscopy for supermassive black holes. These are difficult to interpret because they're biased towards the most luminous objects. And so because there's this connection between radiative efficiency and spin, that imparts a bias. But if you have a larger representative sample, it's easier to interpret and distinguish models. Here I'm showing you 3 different variations of Serotina, where here we have MAD on the left and then sane in the middle. The difference here is that the magnetic fields through the Blandford-Znayak mechanism are extracting some of the spin energy and making the peak at 1 weaker in the MAD case than it is in the sane case. And then in the incoherent case, we're centered around 0 with some width that comes from black hole mergers. The spin distributions are encoding the recent assembly histories in ways that the luminosity functions cannot, apart from pretty subtle differences in the radiative efficiency, and you can always, those are always degenerate with, say, bolometric corrections and obscuration. So this is a much clearer difference between black hole growth channels. Another way to break degeneracies is looking at multi-messenger. And so this gives us some indirect synergy in this science case when it comes to LISA and the multi-messenger community. So when it comes to luminosity functions, one of the main degeneracies is which of these objects is actually accreting and at what rate, and how do you turn m dot into Lx. In this model, we self-consistently produce distributions of LISA events. These are black hole mergers, not including MREs. And here we have differences in the seeding models that are evident in the redshift and mass distributions, where in this case you basically see the initial mass function of the heavy seeds that we assumed. But it's really black hole spins that distinguishes how these masses were actually assembled. And here we have very different distributions for these different kinds of accretion channels as well. With LISA, we're anticipating 1% spin precision and hundreds of mergers across the sky. And this will also link indirectly with the dual AGN science case that is seeing the progenitors of this kind of systems that we'll be hearing about more today as well. So in conclusion, Serotina a semi-analytic model for black hole galaxy coevolution from the seeding epoch to the present, showcases Axis's constraining power. For black hole seeding, we can measure these high redshift luminosity functions to see where the models diverge. For feedback, we're measuring these X-ray cavities where we have different predictions for the black hole feedback from jets. For growth, measuring the black hole spins will really tell us in detail how these masses were assembled. And in terms of dynamics, the dual AGN incidents that Axis will be able to resolve will synergize with the gravitational wave community and break yet even more degeneracies. Thank you, and I'll take questions.
Couple of questions, or we're running a little late.
A very quick question. Angelo, in your model, do you assume any distribution for the spins of the initial distribution for the spins of your black holes at high redshift?
Yeah, the initial spins in this model are actually all at 0. This is actually motivated by our super Eddington prescriptions, where we've seen in GRMHD, if you have higher and higher super Eddington rates, these MAD models will tend to give you an equilibrium spin that's closer to 0. So this is something I think is reasonable. Giving it a little bit of width would not really make a difference. And for most observables, that'll get erased anyway.
Thanks.
Hi, Angelo. Quick question. How well can Serotina predict the amount of obscuration, that the nuclear obscuration that each source will have?
Yeah, unfortunately, I can't predict that at all, essentially. I don't have galaxies directly in this simulation. I'm focused on the black holes. And so that ends up being a prescription.
Oh, okay. No, sorry. I didn't mean the galaxies. I mean the nuclear obscuration. So basically from the material that is fitting the black hole, can you make a prediction?
Yeah, not really. I would need to prescribe that. I have the Eddington ratios, so if you want some like relation between those, that could be implemented, but it would be an assumption.
Great talk, Angelo. Thank you very much. Can you go back to your slide number 7, please?
Sorry, which one?
Number 7, I believe.
7.
Yes, perfect. So do I interpret your figure correctly that if you have coherent accretion, the effect of spin down via jets is minimal, and if you have incoherent, then basically it's completely irrelevant? Or if you were to wedge between the two. I was wondering, how incoherent exactly is your incoherence? Is it isotropic, or is there a switch you can turn in Serotina to model this as a sort of continuous spectrum?
I've taken the limit where the switch between prograde and retrograde is really, really small. And so these are basically the two extremes. So I don't have implemented a switch where you can actually do that, but it would be straightforward to define. They would be very degenerate, as you might imagine.
Thanks.
Thank you so much for the nice talk. So a very naive question for the seeding plot that to distinguish different scenario. Do you need to measure the redshift, black hole mesh, all those properties for the black holes you detected for the in the X-rays?
Yeah, certainly for this particular science case, we need to know the redshifts of each of these. That means that our current plan is to have overlap with our wide and deep surveys with other surveys that can give us first photometric and then spectroscopic redshift follow-up.
Do you need black hole mesh?
Ideally, to break degeneracies. In this case, well, given some assumptions, in this case, if it's just the luminosity function, you don't need the masses. But if you really want to dig into, well, it's possible that super Eddington events could have happened, then you need additional information to break those types of degeneracies as well.
Thank you.
Let's move on. Let's give Angelo the back. Sorry. So we have Mahmudunnobe here to tell us about the evolution of SMBH mass and accretion in the last 10 billion years.
Can you hear me better? Okay, thank you. So I'm Mahmoud. I'm working under Dr. Tonima in Wayne State University, Michigan. Our work is also part of like the Accretion history of AGN, the AHA collaboration. We have like few people here from AHA collaboration. So we're trying to understand how the supermassive black hole mass and the accretion rate both are evolving over like last 10 billion years, which is around like redshift of 2, right? So the Oh, okay. Sorry. Okay, we can skip the background. So, of course, the active relative nucleus when we have a supermassive black hole at the center of the galaxies. This is the current understanding of how the structure looks like. So, the most important part is the broadline region surrounding the accretion disk that differentiate the main classification between the type 1 and type 2 AGN that we have, right? And the unified model of AGN says us that both demographics are actually the similar demographics, but the main classification is happening based on the viewing angle. If we are at an angle where we can see the accretion disk, we can see the broadline region. So it's like unobscured from the dusty torus region, then it's like an unobscured AGN. And if our line of sight is blocked by the dusty torus, then it becomes obscured and we cannot see the broadline region. And of course, it becomes like much more difficult to estimate the black hole properties, especially the mass itself. So what differentiates between how a black hole will become likely, how likely would a black hole will become like obscure or unobscured? So the radiation regulated unified model says that we need to consider the both criteria. One is the luminosity, which creates a radiation pressure. That's like pushing the materials away from the black hole itself, pushing the dusty torus away. But we also need to consider the black hole mass, because if the black hole is massive, it will also like attract the dusty torus around it, right? So ideally, instead of just considering the luminosity itself, we need to consider the ratio of luminosity versus mass, both things, which is can be like considered using the idea of the accretion rate or the Eddington ratio. So we are trying to see in the radiation regulated unified model how this Eddington ratio distribution function changes over time, right? So this radiation regulated unified model got strengthened by the work of like the Swift-Bat data from like Rich's work shows that how at higher Eddington ratio, the fraction of obscured sample like drastically dropped down so much, right? So the same data set, the Swift-Bat 70-month data set, that gives us a very, very completed set of like obscured AGN, because that's the most difficult AGN to detect, right? Because most of the other survey has like sampling bias, selection bias for the obscured AGN. So Ananda et al. In 2022, in their paper, they were able to create this like Eddington ratio distribution function or the accretion rate distribution function for both type of both class of AGN, right? The obscured and unobscured. And they found something very interesting, that at low Eddington rate, yes, they match together. The Eddington distribution function like match relatively well. But at high Eddington ratio, the obscured sample becomes much more like, the number of obscured sample decreased so much, which suggests that a possible scenario that maybe at higher Eddington ratio, those obscured AGN can able to like push the materials away and become unobscured. So it could be a possible transition region, but this work has been only done for the local AGN, so only for like the redshift of less than 0.3. So that's why in our current work, we're trying to understand how this Eddington ratio distribution function, this ERDF, like behaves in the higher redshift, right, up to like redshift 2, and how it changes for like both obscure and unobscure sample. Because if we can see the separations, then that can also give us idea about the time scale of like transition mechanism itself, right? So that's our primary goal. So of course, like we need those 4 variables. That's the most necessary one. We need the black hole mass and the AGN luminosity to get the Eddington rate, and then the Eddington ratio, and then we need the obscuration column density and redshift, all of those things. So we did a completeness study of like 4 of the survey that we 4 of the extra survey regions. So I want to focus one thing here. So the most problematic variables to detect is the black hole mass. So you see for like stability 2x, we have around like 6,000 objects. For Chandra, we have like, from like the Chandra CDWFS, like Whitefield survey, we have like more than 6,000 sources. But we only have like 1,000 black hole mass measured from the stability 2x. And Other than that, for all other survey, we only have an estimate of stellar mass that has been done from the multi-wavelength observation, but we don't have any black hole mass estimate. And the STRAP 82X black hole mass, those are also primarily for unobscured AGN. So we were able to see the broadline region, and that's how they were able to find the mass itself. And that's the most problematic part. So initially for the first project, we focused on those data that we already have the direct black hole mass and like direct AGN luminosity to constrain the ERDF, right? So that's our sample. So we selected almost like 1,000 sample in the STRAP 82X region, but remember that all of them are unobscured. So we'll only have the ERDF for the unobscured one, but not the obscured one. And as you can see, we have like sample, like good enough sample at least up to like redshift of 2, and then the sample size become like less. We initiated a Bayesian IMSIMC approach, so like we're defining a functional form for our distribution function. For example, for black hole mass function, we're assuming a like modified sector function. For the ERDF, we're assuming a double power law, broken power law. So once we have defined functions, then all we need to do is like optimize those function parameters, right? So for example, here, black hole mass has 3 parameters that we need to optimize. So each point in the parameter space represents like different shape of my distribution function, right? So in our approach, the most important part we're trying to consider is the likelihood that like for a given parameter set, how likelihood that the observed data should be able to show. And here we are considering the obscure instrument sensitivity. We have the methodology to like consider different survey by considering like their own like selection function. And then we're also considering how the obscuration like, impacts in this way, and like how the measurement uncertainty, which is like becomes very important, especially at higher redshift. How we can like also incorporate that uncertainty into our likelihood function. So we initialize with a random set of parameter set, and we find out the likelihood, and then we propose a new parameter set. We find out the likelihood of that new parameter set, and based on the likelihood ratio, we either accept it or reject it, and we keep continuing doing it until we reach to a convergence, right? So from this approach, we started using a very uniform prior for all our parameter sets, and we were able to like constrain very like Gaussian looking the posterior distribution for like all our parameter sets. Once we have the parameter sets, that gives us the result itself, right? So I can show you the preliminary results that we have. So this is the preliminary results for the Eddington ratio distribution function. Notice that this is only for the unobscured AGN, right? So the red line shows the unobscured AGN for the local region from the work of in like the SwiftBat data. So this is fixed, and then you see how the blue curve is like shifting slightly over redshift. So one particular thing is at the very first bin where the redshift range is similar for both SwiftBat and STRAP 82X, they should be able to match together at least under the error function, but we are seeing a slight variations, and that's why we try to see how the like histogram of the redshift distribution looks like. And as you can see, for STRAP 82X, most of our data is like is still is skewed towards like 0.3, 0.2 that redshift. So our understanding is because of that difference in the redshift distribution, that's why we have this slight difference in the ERDF itself. So we also compared our results with like some of the other work. So for example, another very prominent work people are doing to constant ERDF, especially when we don't have black hole mass, is using the specific accretion rate. So just taking the ratio of the X-ray luminosity and the stellar mass, assuming that the black hole like scaling relationship will be hold true for like the all redshift. So this is the work from Lalox 2024. So we can see that they also show that the broken region is like shifting over redshift. This is something we are also recovering. But in the lower part of the Eddington rate, they had a very like very like lower slope, and like the uncertainty is also very high. So we were able to like improve in the lower part of the ERDF like significantly compared to like their work. Another interesting thing is in terms of the mass independence, the SwiftBat result shows in local region the ERDF is mass independent for both obscured and unobscured. So using the STRAP 82X data, we found that okay, this is also true for our case until in the local range. But as the redshift going higher, we are seeing there is a deviation started to evolve in the low mass and the high mass sample of the ERDF, right? And this is how our black hole mass function looks like. And in the black hole mass function, we also saw like that. Interestingly, we don't expect to have like that much of high massive black hole, especially in the high redshift. So, but we can see that there is a slight increase happening also with redshift. So that's also one thing we are still trying to understand, that is it necessarily something intrinsic, or this is happening because we have a sampling problem with the black hole mass, because we're only having the sample for which we have black hole mass. So maybe that can add a specific bias itself, right? So now as future work, we are trying to see how we can work with the obscured AGN and how we can use the idea of the multi-wavelength data to estimate the black hole mass through the ACD fitting or the multi-wavelength data set for the obscured AGN. And then we can have a way to like estimate both ERDF of obscured and obscured AGN itself. And of course, like when XS comes up, because of its high sensitivity and like, high resolutions, we'll be able to like find out much more fainter high G sample of like the obscured AGN, which will be able to like reduces a lot of selection bias, especially in the lower part of the ERDF itself. So that's all what we're for now. Thank you so much for listening, and I'll be happy to take any question.
Okay, we
Officially too loud. But I'm happy to pass it around. We have time for one or two questions before the coffee break, but I think that's about it. Anybody?
So this is really interesting and really nice work. So the Stripe 82 type 1 black hole masses. So Stripe 82X is, like a fairly shallow X-ray survey. As you get type 1 black hole masses from some of the deeper X-ray surveys, how do you think that'll kind of change your picture of the Eddington ratio distribution function?
So our understanding is it depends on, for example, let me show this. Yeah. So primarily we were expected to see like more shift into the region where the breaking is happening, right? So we're expecting once we have like more data set, maybe we can able to see is the shifting goes like much more. For example, as you can see, even until 1.2, the shift is very, very limited. We went only from like -1 to like -0.5, right? So once we have like more data, it should be able to like give us more constant on like is the break is actually very significant, or is this only coming out from the measurement uncertainty or something like that. So most of the things we still don't know yet. So once we have more data, then we will able to like interpret it accordingly.
Okay, great. Let's get Mahmoud a big hand. We'll take about 15 minutes.